I'd like to talk through how to answer question 5 on January 2013 Ph1 paper, which is a question that's largely about moments. And the setup is we've got a solid block of uniform density resting on a sloping rough surface. The fact it's a rough surface means that it's not going to slide, that there is going to be a large frictional force. And the diagram here shows it at the point of toppling. The idea behind showing it at the point of toppling is that if we were to angle the slope up any higher, then we would have gravity acting so that the weight of the object was outside of the corner of the object, and the object would fall over and roll down the slope. The first question on the paper says, what is meant by the centre of gravity? The centre of gravity is simply the point at which the entire weight of the object appears to act. Take note that when answering this question, you've got to say it's where the weight appears to act, not about where the mass appears to act, because the question is asking about the centre of gravity, not about the centre of mass. However, these points will be coincident. The next part asks us to calculate the angle theta, i.e. the angle of the slope, assuming that no sliding occurs. So this is the setup, and we can extend the line showing where the weight is acting all the way through the centre of mass and up to the opposite corner. We then know that this line here has got a length of 60 centimetres, and this line here has got a length of 40 centimetres. And hopefully you can see that that angle there is going to be theta. So now it's just a case of some quite straightforward trigonometry. We say that tan theta must be equal to the opposite over the adjacent, and then we find out that theta equals 33.7 degrees by taking the inverse tan of 40 over 60. This block is then suspended on the end of a long rod, with the rod being held up by a string which has a tension T in it, as shown in the diagram. And we're told that we can ignore the weight of the rod because it says that it has negligible weight. If we weren't able to do that, you would just take the weight of the rod to be acting at the centre of gravity of the rod. But we don't have to do that. The first part of the question, though, says find the mass of the block, given that the density of the block is 400 kilograms per metre cubed. It's quite straightforward, but the thing to note here is that we need to convert our centimetres, which is the way that the dimensions of the block are given at the start, through into metres. So what we're going to have is the volume is 0.6 metres by 0.4 metres times 0.1 metres, which comes out to 0.024 metres cubed. We then know that density is given by mass over volume, so we can rearrange that to get mass equals density times volume, which is going to be 400, which is the density, times 0.24, which is the volume. Oh, correction, that should be 0.024, which is 9.6 kilograms. Then says, by taking moments about the hinge, calculate the tension in the string. So we've got the tension T in the string there. And perhaps the most straightforward way to see this is that we could draw a right-angled triangle up like that and resolve the tension horizontally and vertically. Now we know that moments always have to be taken, the forces acting perpendicularly to the pivot. So here, the only force that we're interested in is that one there, marked with the double arrow. and that is for the tension. If we want to find out what that is, well, we can see that that angle there is going to be 50 degrees, so this must be T cos 50 degrees. And the size of that must exactly balance out the weight of our object acting down there. So now we've got T cos 50 degrees acting upwards times the distance away from the pivot that it is, which is 1.2, and that's going to be equal to the weight of the object, mg, which is 9.6 times 9.81, acceleration due to gravity, times the distance away that is, which is 1.8. So we've taken moments about the pivot there and in order to find t. If we rearrange that, we will find that t comes out to be equal to 220, and being a force, it's in newtons. The final part of the question asks us to calculate the horizontal component of the force that the rod exerts on the hinge. So here, it's the 40 degrees we're interested in, and it's the force acting in that direction there. So that is going to be T cos 40 degrees. Notice that although we're using cos again, we've got the cos of 40, not the cos of 50. So we're going to say that F equals T cos 40 degrees equals 220 times cos 40 equals 169 newtons.